Your roof is actively trying to kill you every single summer. Not the sun, not the heat rising off the asphalt outside. Your own roof, absorbing solar energy all day long and pumping it straight down into the space where you live, sleep, and breathe. And there is a white powder sitting on a shelf at your local hardware store right now, a powder that costs less than a cup of coffee that shuts that process down almost completely. The ancient Greeks figured this out over 3,500 years ago and never needed a single machine to survive scorching Mediterranean summers. Today, we're going to show you exactly why a $2 powder beats a $3,000 machine, and the answer lives entirely inside the laws of physics. Welcome to Wild Survival. If this channel isn't already part of your weekly routine, right now is the moment to change that. Hit subscribe. Because what we teach here isn't found in instruction manuals or product brochures. It's the knowledge the natural world has been running on for millions of years, and the stuff certain industries would rather you never learn. Now, let's talk about what's actually happening above your head. Picture a desert tortoise, flat shell, broad surface area, baking under a relentless sun in the Mojave. That tortoise has a problem every living creature in a hot environment has: too much solar energy landing on its body and turning into heat it can't escape. So what does it do? It doesn't fight the heat from the inside. It manages what happens on the outside first. The shell's texture, its color in some species, the angle at which the animal positions itself, all of it is designed to handle energy before that energy becomes a thermal problem.
The tortoise isn't running a cooling system internally at full blast while ignoring what the sun is doing to its exterior. It starts with the surface. Your house is doing the exact opposite of what the tortoise does, and the air conditioning unit you've been relying on is the machine version of a tortoise trying to stay cool by furiously panting from the inside while leaving its dark shell aimed directly at the midday sun. Here's the physics most people have completely backward. Your air conditioner does not create cold air and push it into your home. What it actually does is grab the heat that already exists inside your living space and transport it outside. It is a heat mover, not a heat blocker. That distinction matters more than almost anything else in this conversation. Because while your machine is working hard to pull heat out through one side of the building, your roof is pouring heat in through the top at a rate that overwhelms everything the unit can do. A standard dark tile or slate roof absorbs between 85 and 95% of every unit of solar radiation that strikes it. That absorbed energy converts directly into heat, conducts through the roofing material, and radiates down into the space beneath your ceiling. In warm climates during summer, the temperature in that attic or underroof space regularly hits 140 degrees Fahrenheit. That thermal mass then bleeds downward into every room in the house around the clock, not just during daylight hours, but all night long, because the structure itself has stored the heat and is releasing it slowly into the space where you're trying to sleep. Your air conditioner isn't losing a battle against the temperature outside your walls.
It's losing a battle against the thermal bomb sitting directly above your head. We're going to call this the solar load trap. The moment sunlight hits your dark roof, the clock starts running. Energy converts to heat. Heat moves into your structure. Your cooling system kicks on to compensate. And it never fully wins because the source of the problem is still there, absorbing, conducting, and radiating every hour the sun is up. On the hottest days of the year, your system runs almost continuously, not because the outdoor air is too warm, but because the roof overhead is functioning as a slow-release heat furnace. Before we go further, here's something we want you to actually think about and drop in the comments below. What is your best guess for what you spend on electricity to run your air conditioning each summer? Not the unit itself, just the power bill. Write that number down in the comments. By the time this video ends, you're going to see exactly how much of that cost was never necessary. Now, what did the ancient Greeks actually figure out, and why does it work? Every surface on Earth has what physicists call a solar reflectance index. It's a number that tells you what percentage of incoming solar radiation bounces back into the atmosphere rather than getting absorbed into the material. A dark slate roof has a solar reflectance index somewhere between 5 and 10. That means it captures 90 to 95.
Even at 80% reflectance, the remaining 20% of absorption on a large surface area is still a significant thermal load. A 1,000 square foot roof under a summer sun is still absorbing the thermal equivalent of 2 to 3 kilowatts of continuous heat, even with standard white paint doing its job. That is not a solved problem. That is a partially reduced problem with a very large remainder. Hydrated lime, calcium hydroxide, the same material that Mediterranean builders were mixing with water and brushing onto stone surfaces 1,500 years before the birth of Christ, reflects between 95 and 98% of incoming solar radiation. That is not a reduction in heat absorption. That is the near complete elimination of it. And a bag of it, weighing 44 pounds, costs between $2 and $4 at any hardware store in the United States, Mexico, Colombia, or Argentina. Think about what an octopus does with its skin. An octopus can shift its skin texture and color in under a second, not for camouflage alone, but to manage how much energy it absorbs or reflects in its environment. It is running active reflectance management on a biological level that makes your white paint look like a rough draft. Hydrated lime is the closest thing a building has to that biological capability, and it's been sitting on the hardware store shelf the entire time. Researchers at Lawrence Berkeley National Laboratory tested the mechanism directly. They applied a mixture of limestone powder and water, the identical recipe that Greek builders had been using for 3,000 years across the entire Mediterranean basin, onto a flat rooftop surface.
The surface temperature of that roof dropped by nearly 40 degrees Fahrenheit compared to an identical dark roof positioned right beside it in the same sunlight. Interior building temperatures dropped by 7 to 9 degrees Fahrenheit. The test building required no mechanical cooling during the entire period of the study. So why isn't every roof in Arizona, Texas, Florida, and California covered in this material right now? That question has an answer, and the answer isn't an accident. In 2021, Professor Xiulin Wan at Purdue University set out to build the most reflective paint surface ever recorded by modern science. He wasn't specifically studying lime. He was exploring the theoretical ceiling of what ultra-high reflectance coatings could do to building temperatures if pushed to their absolute limit. The formula he arrived at uses barium sulfate particles engineered to scatter light across every solar wavelength simultaneously, producing a surface that reflects 98.1% of all incoming solar radiation. The Guinness World Records certified it as the whitest surface ever created by human beings. The peer-reviewed study published in ACS Applied Materials confirmed the numbers held under full scientific scrutiny. And here is the figure that made the thermal coating and air conditioning industries extremely uncomfortable. Ruan calculated that coating 1,000 square feet of rooftop with this formulation produces 10 kilowatts of continuous cooling power. A standard residential air conditioning system operates at an output capacity of between 3 and 5 kilowatts. The passive coating outperforms the active machine by a factor of 2 to 3, while consuming exactly 0 watts of electricity.
Now, here is what connects Ruan's ultra-white paint back to the $2 powder in the hardware store. The physics driving both materials are identical at their core. They both work through two specific mechanisms that your air conditioner doesn't use at all. Mechanism 1 is short-wave solar rejection, bouncing visible sunlight and near-infrared radiation back into the atmosphere before it ever converts into heat inside your structure. The energy never enters the building. The building never has to deal with it. Your air conditioner cannot do this. It can only respond to heat that has already gotten inside. Mechanism 2 is long-wave infrared emission, also called radiative sky cooling. This is where things get genuinely fascinating and where most people have never taken the physics far enough. Highly reflective surfaces don't just block incoming energy. They also actively radiate stored heat upward into the sky, even during peak daylight hours. The sky above you, particularly the upper atmosphere, is a thermal sink, operating at temperatures approaching negative 455 degrees Fahrenheit. When a surface is engineered correctly, it radiates its stored thermal energy directly upward toward that sink, not sideways into the warm outdoor air the way your air conditioner exhausts its heat, but straight up toward expectively the coldest environment that exists anywhere in the known universe. Ruan's test surfaces measured temperatures below ambient air temperature even during the middle of the day. The surface wasn't just blocking incoming heat, it was actively dumping stored heat into the atmosphere above it, pulling its own temperature down below the surrounding air in full sunlight. Let that land for a moment.
Your air conditioner expels heat into outdoor air that may be running at 105 degrees Fahrenheit on the worst day of the year. It is fighting a thermal battle against air that is nearly as warm as what it's trying to get rid of. The lime-coated roof is expelling heat toward a sink at negative 455 degrees. The contest isn't even close. We're going to call this the sky dump advantage,
And it is the reason why ancient Mediterranean civilizations executed this strategy at massive architectural scale for thousands of years without ever once needing to understand the thermodynamics behind it. They just knew it worked every single time, without fail, without machinery, without fuel. Now let's talk about what this means economically and why certain industries have had very strong financial reasons to ensure that most American homeowners in 2025 have never heard the term lime wash used in the context of building cooling. The global air conditioning market generates over $130 billion per year. The global paint and coatings market generates over $200 billion per year. Hydrated lime is a commodity material. It cannot be patented. You cannot trademark calcium hydroxide. You cannot build a subscription model around a powder that costs $2 a bag, lasts for years on a treated surface, and reduces air conditioning usage by 60 to 70% in high heat climates. A lime-washed roof doesn't just hurt paint company revenues. It directly attacks the foundational income model of the entire mechanical cooling sector.
Homeowners associations in dozens of American cities and municipalities across the Sun Belt have explicit rules governing roof and exterior colors, rules that require earth tones, dark tiles, muted surfaces. Builders in high-heat markets default to materials and color codes that, mathematically, maximize solar absorption and guarantee that the climate control systems in those homes will run at full capacity for 4 to 6 months every year. A skeptic would call those rules aesthetic preferences. The mathematics calls them something considerably less neutral. This isn't a conspiracy that required a secret boardroom meeting. It only required an industry whose financial model depends on you not knowing that the Greeks solved this problem before the Roman Empire existed, with stone dust and water. Now let's go one level deeper, because here is where most people stop, and stopping here leaves half the physics untouched. Think about a thick-walled adobe structure in New Mexico. The walls are massive, dense, heavy. During the day, those walls absorb solar energy and heat slowly. But because the mass is so enormous, the energy takes 8 to 12 hours to conduct all the way through, so by the time it reaches the interior, the outside air has already cooled down for the night and you can ventilate it out. That's thermal mass working in your favor through intelligent design. Now think about what happens in a standard modern American home with thin walls, dark exterior paint, and a dark roof. The walls heat up fast. They don't have enough mass to delay the thermal wave significantly. The heat moves quickly through the structure and arrives inside the living space during the hottest part of the afternoon.
Then, because the mass is relatively small, it releases that stored heat all night long, keeping your interior warmer than the outside air for hours after sunset, making your air conditioner run through the night to compensate. We call this the thermal mass trap. And the fascinating thing is that a perfectly reflective roof alone doesn't fully solve it. Your walls are still absorbing solar radiation all day. The east and west faces of your home are getting direct sun at the highest intensity angles during morning and late afternoon hours. The ground around your foundation is a thermal reservoir that bleeds heat upward through your slab continuously. The thermal mass trap operates on every exterior surface simultaneously. The builders who refined lime-wash architecture across the Mediterranean didn't just paint their roofs white, they painted everything white. Every wall, every face, every exterior surface of every building in every village. The physics of that decision compounds rapidly. A south-facing wall painted dark absorbs solar radiation all day and radiates it inward through the afternoon and evening, functioning as a slow-release thermal battery that works directly against your comfort. The same wall treated with lime at 95% reflectance converts that same sun exposure into nearly zero heat gain. The battery is switched off. Multiply that across all 4 exterior walls plus the roof, and the thermal mass trap loses most of its power over the interior of the building. The structure simply isn't accumulating the thermal energy it would need to radiate back inward overnight. The practical priority order for a standard American home is this.
The roof comes first because it receives direct overhead sun at maximum intensity for the longest duration of the day. The south-facing wall is second, longest arc of direct exposure in the daily solar path. East and west walls matter most during the morning and afternoon peak hours, respectively. And the total material cost to treat every exterior surface of a standard single-family home with hydrated lime sits well under $100 for most properties. That is the number that makes the $3,000 air conditioning installation feel like a deeply reconsidered investment. So here is exactly what you do with this information starting today. A 44-pound bag of Type S hydrated lime, calcium hydroxide is the compound you're looking for on the label,
costs between $2 and $4 at Home Depot, Lowe's, Menards, or any independent hardware store across the country. It is the same compound that has been the active reflectance agent in Mediterranean building practice for 4,000 years without a single formula modification. Mix 1 part lime powder with 2 parts water until you reach the consistency of thin paint. Not paste, not mud, not water. That consistency is called a lime wash, and it is the exact formulation that has been proven across centuries of applied use in some of the hottest inhabited climates on Earth. Apply it with a long nap roller or a wide brush over a clean, dry roofing surface in 2 complete coats, allowing the first coat to cure fully overnight before applying the second. The first coat seals and bonds. The second coat delivers the full reflectance performance.
The total material cost for treating 1,000 square feet of roofing surface, a typical footprint for a standard American single-family home, runs between $15 and $30. A homeowner in a high heat climate who applied this formula measured the under-roof space temperature before and after treatment. Before lime wash, 145 degrees Fahrenheit at peak afternoon. After lime wash, 97 degrees Fahrenheit at the same time of day. A 48-degree drop in the space directly above the living area with 2 bags of powder at an afternoon of work. Interior living space temperature dropped 11 degrees Fahrenheit without running the air conditioning at full load. Estimated electricity savings for that single cooling season exceeded $800. Compare that to a new air conditioning installation ranging from $3,000 to $12,000, plus $150 or more per month in electricity costs every cooling season. The desert tortoise figured out passive thermal management before mammals existed. The ancient Greeks turned it into architectural practice before they had a written alphabet. Professor Ruan validated the exact mechanism in a peer-reviewed laboratory setting in 2021. And the material has been sitting on the shelf at your hardware store the whole time. $2 a bag, available to anyone who knew to ask for it. The most expensive square footage in your home has always been the surface facing the sun. Now you know exactly what to do about it. You now understand why passive solar rejection outperforms mechanical cooling at the most fundamental level physics allows.
But there is a deeper survival question that almost no one asks until the moment they actually need the answer. What happens to your home's internal temperature when the power grid goes down in the middle of a heat wave and your air conditioner stops running entirely? The physics of that survival scenario and the architectural principles that kept people alive without any electricity at all are exactly what we're breaking down next.